Hey everybody! Today I'm going to teach you about linear momentum equation. So on the previous video, I taught about the principles of fluid mechanics. So if you did not watch that or you don't understand what that is, you have to understand that to understand this. So it's better that you watch that one first. And yeah, we can start now. So why do we use the momentum equation? So it comes from three things, okay? Because of Newton's second law, F equals ma. So we can determine the forces acting on a steady state flow. So remember what a steady state flow is. It's a flow where the condition of a fluid at any fixed point does not change over time, okay? So that's why we use F equals ma. And also second thing is Newton's third law, which is for every action there is an equal but opposite reaction. This is used to find the reaction force from the wall, okay, of the flow. So it's produced by the flow in the, so if in the pipe, for example, there will be some reaction forces from the pipe onto the flow. And third thing, the control volume approach. So I've talked about this in my previous video, and I tried my best to explain it in the best way possible. So we are going to be using this throughout the whole video. Now, first of all, Newton's second law. Now, I am really bad saying words, big words, okay? The system view, which is Lagrangian, whatever that is, okay? All that matters, we understand what it is. So we know how to calculate momentum, which is mass times velocity, all right? And then any change in velocity, so that does not just mean the speed, no, magnitude and direction. I've made a video about statics that explains to you if you don't understand. You should be understanding that anyways. So this results in change in the particle's momentum. Change in momentum is very important here. So this is where we use F equals ma, because we know that momentum is mass times velocity. Now, if you want to find the change in momentum, we divide it by time, which gives us mass times acceleration, okay? So it gives you the force. Now, what happens when we are comparing system versus control volume? Now, the system approach is like when the fluid, like, it tracks a fixed part of fluid as it moves. So it's very easy. It's useful for deriving the second law, and the law of Newton's fluid law, if you've seen the previous video. But when it comes to engineering flows, it's different, okay? So if you are doing engineering or someone who wants to be an engineer, we don't use this one much. Instead, we use Newton's second law for control volume, okay? So this is practical on an everyday approach. It's easier, easier maths, and we're gonna talk about it now. So we know that in a control volume, we use a second law as a continuity equation, and also Bernoulli's approach, that m dot, the mass flow rate, equals rho Ca1, and which equals rho Ca2. In a nutshell, that means when you have a control volume, when the fluid goes into the volume at the initial point, subscript 1, the total mass flow rate, okay, should equal the same at the end. Okay, that's the law of conservation. Now, we use something called momentum flux, which is the rate at which momentum passes through a control surface. Okay, which we calculate it using rho Ca times c. C is velocity, A is the cross-sectional area, rho is the density. that is just the mass flow rate times velocity, okay? And in that way, the rate of change through the control volume, we can also say it's going to be the same, okay? So what we would do, we would bring the equation for the mass flow rate, okay? The control volume view, and then we will get instead use momentum flux, the subscript 2 moment. I'm gonna call it subscript 2, so the rho 2 c2 a2 c2 minus the subscript 1 as a momentum flux should equal to the following: rho ca and then bracket, because you are simplifying it, putting it like factorizing it, and then we know what m dot is, and then yeah, it just simplifies. Now, what we get for the result is sigma f, which means the sum of the forces should equal to the mass flow rate multiplied by the final velocity minus the initial velocity. Now, this equation gives the increase in moment per unit time, because force is momentum divided by time, okay? Because we go from mv to ma because v is over t. You know what I mean, right? Uh, in the direction of motion. So Newton's second law says that a force is required to produce a change. Therefore, we get this equation that we have been talking about, the result. So this states that the net force acting on the fluid within CV equals the rate of change of momentum flux of the fluid. So, also sorry, I said CV and I didn't explain what CV. It's just shortcut for control volume. So yeah, in general, we just got the net force exerted on the fluid in a given direction is equal to the rate of change of momentum flux. Okay, because this equation is a vector, force is a vector, the force is assumed in the positive direction, in which velocity is assumed to be positive, okay? So that's something we do a lot with vectors. Now, force, wall reaction, and pressure. So we talked about this in the first two slides. This is what we are going to talk about now. When you have a control volume and a fluid goes through, it makes, just as we said about third law, Newton's third law, the fluid makes a reaction to the wall of the control volume, and then you get a reaction force, okay? So forces due to momentum change will equal to force on the fluid due to the wall plus the pressure force. So there's also pressure force in there, okay? So what that means is the total force Fm due to momentum change is equal to Fu, which is due to the wall, plus Fp, pressure force. So how do we get this? Is using our previous video, the equations, how we found out with what Fp is. And so Fm, in a nutshell, equals m dot out, so that's m dot 2, whatever the mass flow rate is when it's coming out, times the velocity when the fluid is going out, minus the input, the same thing but the input one when it's getting in, okay? And then Fp is just P1A1 minus P2A2. And then since we got Fx, okay, we get Fx and Fy. Fx is in the horizontal direction. You also get the, yes, you get the y as well. So Fw, okay, is force on the wall, okay, so which equals to Fm minus Fp. All of this is just rearranging equations. I don't want to make it sound like it's a bit very complicated, but yeah, then you end up with Fx being Fp plus m dot C2 minus C1, okay, which is Fm. So Fx equals Fp plus Fm, okay? Right, so the reaction force we call it FRX, so that's Fx, but reaction, okay? What we do is that we do the same, is just Fx, but it's the opposite, okay? It's the opposite, so it's in the opposite, it's, if it was positive, it becomes negative, okay? That's what we mean by it, okay? So now, what about like a 2D flow, okay? Now, why did I say Fy can also exist? The previous example we were talking about was completely horizontal. We did not have that at an angle. This one, okay, the tube or whatever we have, the control volume or control surface, because this is 2D flow, okay, is angled, right? Is angled at uh, angle alpha and theta, okay? Now we have to first assume some stuff, steady state flow, okay? Uniform flow at control surfaces, and that C1, okay, which is the velocity, and C2 are both normal to their respective control surface, okay? So where the C1 and C2 comes in should be perpendicular to their control surfaces. Now, we are going to resolve for fx and fy, okay? So we will use the previous principle that we've learned, which is the force due to momentum change is equal to force on the fluid due to the wall plus pressure force again. Now here, instead of x, we have y, okay? So now we are going to use resolving forces using trigonometry. I'm not going to get deep into it. You could, if you are someone who loves maths a lot, I love maths, but I prefer keeping it short, honestly. Now, what we do is that we use the same equation we did for fx on the previous one, except for fy, we multiply, okay, we get m dot 2 c2 multiplied by sine alpha, and then minus m dot 1 c1 multiplied by sine theta, and then you plus that with the p2a2 sine alpha minus p1a1 sine theta. It's the same thing as the previous one, except we added sine alpha and sine theta, because when it enters, it's at a different angle to when it gets out. Now, fx is the same thing, except we change the sign to the cosine. That's again because of trigonometry, okay? Now, it's better that, now, how I always remember this is I combine the equation we already learned for a 2D, where you got it completely horizontal, it's not angled, where you don't need to put in sines and cosines, but when you get an angled one, always vertical when it comes to triangles and stuff like that, is going to be sine. And how do we decide if it's sine alpha minus sine theta is which one is the output? Now, you see that it enters, if it enters at the angle of theta, then it will be multiplied by the initial values of m dot 1, c1. If it exists at angle alpha, then you multiply with a subscript 2 ones, okay? So you have to find the difference between these, and then you add it with your pressure force, and you find the difference between these as well, okay? And then the fx is just the cosine version. Right, now dropping the pressure terms. So what does that mean? So we are removing the pressure forces. Why? Now for external flow, we will assume all pressures are the same and drop them from the equation. So now we no longer have the pressure force, okay? Because if we are talking about external flow, that's what happens. Now, what if we want to find the resultant force, okay? So when I say resultant force, I mean the magnitude of the force, because when we get Fx and we get Fy, we get the force at the horizontal and vertical direction. Okay, so we use Pythagoras just like any other trig. Okay, if you're good at trig, you will understand what this is. And then direction, you do arctan of Fy over Fx. Okay, now again, because of Newton's third law, this is going to also mean that the force coming out from the wall, so the reaction force, should be the same but in the opposite direction. Now, if we have a big question where we know we are going to apply the momentum equation, how would we tackle this problem? So first of all, this is always, whenever it comes to aerodynamics and thermodynamics, or fluid mechanics, whatever you want to call it, you always have to define the control volume. Just like, in statics, you always start with a free body diagram. That is the rule here when it comes to fluid mechanics. Define the control volume, and define if the coordinates and positive x and y axis. Okay, then we know the momentum equations. Okay, we write down for x and y, depends. If we do have an angle, then we do x and y. If we don't have angles, it's just x. Okay, then we have to know, is a body force important, like weight of fluid and its container? Most of the times I don't think. Then is the pressure important? So are we talking about external flow? If not, then the pressure is important. So then we will have to use Bernoulli's to find the pressure. Is the flow rate or velocity known? If not, then use a continuity equation. See, sometimes you might not have all the numbers you need to find the forces using the momentum equation. So you will have to use either Bernoulli's or continuity equation. Again, I've talked about this in the previous video, so you could watch it to understand what these two are. And then what we do is calculate the force acting on the fluid using all of that information. Then we can know what is the reaction force from the solid boundaries using Newton's third law, which is just the same as number 6, except it's the opposite direction. Okay, now what about if the boundary is moving? Now that is very interesting. So what we would do, okay, what happens here is when you have your solid boundary, okay, moving with a uniform velocity, usually we put a CV, okay, as the V as the subscript, okay. And when we say uniform velocity, there's no acceleration, because if there is acceleration, actually, it makes it even more difficult to understand. So what we do is we satisfy the steady state assumption using relativity. So we are thinking, okay, the velocity, if like you think about it, if there is an observer standing on the boundary itself, so we are going to think what the velocity will be seen if someone was on that. So it's being relative, okay? Same thing goes with flow rate, which also must be relative, measured relative to the moving boundary. So let's think of a practical consequence, okay? If you have a jet, okay, and the velocity of this jet is c, okay, it strikes a boundary moving at cv in the same direction, okay? So the effective or relative velocity used in the momentum equation will be the velocity of the jet minus the velocity of the boundary. So c minus cv, not just c, okay? Now, propeller theory. Now we have talked about what if the boundary is moving, right? Now we can understand the propeller theory. To work out the theoretical propeller efficiencies, we applied 3 tools, already covered, okay? Force momentum equation, continuity equation, principle of efficiency, okay? Efficiency is how efficient power is, okay? So we also have assumptions here. We ignore the flow rotation. So there's always going to be some rotations in the flow. The pressure upstream and downstream equal to the static pressure of the undistributed flow. Settled, so one-dimensional flow at inlet, and fluid density is constant. Now, the actuator disk control volume. Remember we said we are doing 1D, one-dimensional analysis. This is very simplified. When we have velocity going in to a propeller, like into this control volume, okay? And then we have a propeller disk as our boundary, okay? So it's moving, and then you also have the walls of the control volume, okay? Now, we want to know the force exerted onto this plate or disk. Now, what we would do is we would find the flow rate using Q equals pi r squared because it's circular, that's the area, multiplied by V2 minus V0. Now we are going to be deriving thrust. We are going to still be thinking of 1D force momentum equation, very, very simplified. We want to find the force on the fluid, which is going to be the outlet momentum flux minus the inlet momentum flux, as you see in the equation. Sum of Fx equals the following. Now, how do we find the sum of the input, so inlet momentum flux? It is going to be rho V0 squared R squared. And then the output is going to be rho VO V2 R squared plus VO squared bracket R squared minus little r squared. This is where big R is a full disk radius and small r is the jet radius. Okay, that's some new variables that has been into this. Then you get the final equation of Fx, which is rho r squared, V0 equals V2 minus V0 squared. Sorry, no squared. And then we get to the famous thrust equation. Thrust equals m dot times the change in velocity. Okay. And thrust, power, and propulsive efficiencies. We already found out how to find thrust. Now, how to find power imparted to the fluid. W is work done. Power is change in work. W dot is power. And then that will equal to the outlet mass flow rate multiplied by the outlet velocity squared over 2 minus inlet velocity squared over 2. Then we got the propulsive power, which is thrust times flight velocity. Now, efficiency is the ratio of propulsive power to the power imparted to the fluid, okay? Which means efficiency P, okay, will equal V0 m dot 0 multiplied by V2 minus V0 divided by m dot 0 and the following. Now you'll ask me, how did I get that from? That is, I got that from the thrust times flight velocity in the beginning before dividing, and I wrote the thrust equation and I substitute it into the T, which is m dot V2 minus V0, and then when we divide it, the thing that we're divided it with is the power imparted to the fluid. Then we get the simplest form of it, 2 divided by 1 plus V2 all divided by V0. So this is the final slide, is the fraud efficiency. This is like, we just talked about the efficiency. This is called the fraud efficiency, which is calculated the same way, to divide by 1 plus V2 over V0. It's very cool when it comes to explaining about propellers, because the less the propeller accelerates, the higher the fraud efficiency. And this is actually why we have large, slow turning propellers, because they are more propulsive than propulsively efficient than small and very fast accelerating one. Except there's a problem here, that the less the acceleration per unit mass, that means you will have to use larger propeller or fan. So therefore that's why we use the larger ones, because it's more efficient in terms of propulsively efficient. So this is the end, and I really hope you understood and this video helped you. Thank you so much. Have a very lovely day.